so consider that y equals, let's say, b plus x. This is an addition function, right? Whatever x is, we add it to b, which is a constant, and we get y. If we switch the values of x and y, we call this the inverse function. And we call this the inverse function because now if we solve for y, and we'll do that by subtracting b from both sides, we will get x minus b is equal to y. And I can rewrite this the other way, right? I can flip them about the equal sign, x minus b. And so we can say that if we know what x is and we add b to it, we can find y. And the inverse of that would be to take x and subtract b, and then that would give us y. And so, for example, let's say that y equals, let's let b be 1, okay? Let b be 1, and we're going to be adding x, right? So if we look at this function, if x is, let's say, 0, 1, 2, or 3, when we add 1 to x, we're going to get 0 plus 1, which is 1. That'll be the value of y. 1 plus 1 is 2. 1 plus 2 is 3. And 1 plus 3 is 4. Right? This is the original function, the addition function. Now let's look at the inverse function, that y equals x minus b. And so again, let's let x be 0, 1. Actually, I'm sorry. Let's let x be 1, 2, 3, and 4. And if we plug these values in, and I'm sorry, b is going to be 1, right? The same as it was here. Let's let b be 1. If x is 1 and we subtract 1, y will be 0. And when x is 2, when we subtract 1, y will be 1. And if x is 3 and we subtract 1, y will be 2. And if x is 4 and we subtract 1, y will be 3. And so you can see that if we knew the value of x, 0, 1, 2, 3, we could find y, which was 1, 2, 3, 4. The inverse function says that x is now these values, and we are finding y, which was the original x values. The point of this is that the inverse function is the opposite function of the original function. When we plugged in 0, 1, 2, 3 into the original function, we got 1, 2, 3, 4. When we plugged in 1, 2, 3, 4, we got the 0, 1, 2, 3. So this function undid this function. They're inverses of one another. And that's going to be important for us when we're looking at exponential functions. And so our exponential function comes in the form of y equals b to the x. Right? That's our original function. And if we do the same thing that we did here, we will swap the variables and say that x is equal to b to the y. Now our goal is to find the inverse function is to solve for y. That's not going to be very easy to do. We could try some things with square roots possibly, or the y-th root, right? The root with an index of y. We could try things like that, but we're not going to get very far. And so we need to be able to define the inverse function in another way. And so let me start by saying that our original function here was the exponential function. This was our original exponential function. This is what we call the logarithmic equation. Logarithmic equation. And specifically we say that this is an exponential form. Okay, so we had our original exponential function, and this is the logarithmic equation, but it's also an exponential form. This logarithmic equation is the inverse of this one. Whatever values we plug in for x, we should be able to find y. Just like when we plugged in x here, we were able to find y. This function is supposed to undo this one. They're supposed to be opposite functions, just like addition and subtraction are opposites, right? They're inverse of one another. And so since we can't really solve this very easily, we need to define a logarithmic equation in another way. And what we want to say is that if we were to be able to solve this equation for y, we would get something that looks like y equals log base b of x. And this is how we're able to solve this equation for y. right? And so again, this isn't very easy to solve. Y is in the exponent. To get this out of the exponent and then get something that says y equals is not very easy to do. So we need to define it in another way. And we do that by saying that y equals log base b x. Now, let me give you an example. Let's say that for the logarithmic function here, let's say that x equals, I'll let b be 2, right? I don't want it to be 1 because that's not going to be very interesting. 1 to any power is always 1. So I'm going to let b be 2. If x is equal to 2 to the y power, let's see what happens when y is, how about 0, 1, 2, and 3? What will x be? So 2 to the 0 power, when y is 0, 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. Right, so I'm able to solve for x when I know y. And let's see what happens in the logarithmic function. Now we're saying that y is equal to the log b, which is the base. In my example, the base is 2, right? That's what b was. That's where b falls in the formula. The base is 2. Y is equal to log base 2 of x. And so if we were to look at this function in a logarithmic form, again, we can say that, let's say that now we know x. X is 1, 2, 4, and 8. We should be able to use log base 2 of x to figure out what y is. And we already know what y is when I plug in these values for x, right? These are equivalent functions. And so let's see what this is asking us for. So let's let x be 1. When x is 1, we're saying that y equals log base 2 of 1. And the logarithm is asking us the question, 2 to what power is equal to 1? 2 to what power is equal to 1? And so this is equivalent of saying 2 to some power, the y power, is equal to 1. And so what number would we plug in for y so that 2 to that power is equal to 1? The answer is 0. 2 to the 0th power is equal to 1. Okay, and likewise, let's say that y is equal to log base 2 of 2. Right? Now we're going to let x be 2. And so again, this is asking us 2 to what power is equal to 2? Right? 2 to what power is equal to 2? The answer is 1. And then same thing. Here we're going to say log base 2 of 4. And we're saying 2 to what power is equal to 4? Right? 2 to what power is equal to 4? The answer is 2. 2 to the second power is equal to 4. 2 to what power is equal to 8? The answer is 3. Right? 2 to the third power is equal to 8. And so the logarithmic function allows us to plug in values for x and determine what y is. And when we see the logarithmic function, we're asking 2 to some power is equal to this number. Right? This is the base, this is the argument of the logarithm, or the power, and this is going to be the exponent. Y is the exponent. And so that's what we see exactly right here, where b is the base, in the logarithm, y is the exponent, that's what we're looking for, that's the value we don't know, and x is the power. Right? So b to some exponent gives us this power. And we're asking, well, what is the value of y that gives us that power? So this is the definition of logarithmic functions. This is example 1. It says, write each equation, which is currently in exponential form, and write it into a logarithmic form. And so we've been given these 5 equations. They're in exponential form. And so we can agree that 2 to the third power is 8. 5 squared is 25. Hopefully we can agree that 4 to the negative second is 1/16. Remember that 4 to the negative second is the same thing as 1 divided by 4 squared, which is 1/16. 36 to the 1/2 power, that's the same thing as the square root of 36, which is 6. And p to the q equals r. We don't know the values of p and q or r, but p to the q power is going to be equal to some other value. We'll call that r. And so we want to write these into logarithmic form. And so remember that the exponential form and the logarithmic form are the exact same functions. They say the exact same thing. Whatever value we have here for x and y and b are the exact same values that we can have here for x, y, and b, and both will be true. So all we have to do is identify what value is x, which value is b, and which value is y, and then write those values in the logarithmic form. So here, y is 3, right? The exponent y is 3. So over here, y will also be 3. Now b is 2. So over here, b will also be 2. And over here, x is 8. And so over here, x will also be 8. And so log base 2 of 8 is asking us 2 to what power is equal to 8? And the answer is 3. 2 to the third power is 8. Okay, and so all we have to do is rearrange the values in these exponential forms into a logarithmic form. And so we will say that 2, which is the exponent, is equal to log base 5, because that's the base of the exponential, of 2. No, I'm sorry, 25. 25. And so this is saying 5 to what power is equal to 25? The answer is 2, because 5 to the second power is in fact 25. And so we can do this for all of these. Again, y, over here y is the negative 2, is equal to log of a base, and over here the base is 4. And then x, the answer is 1/16. So we're saying 4 to what power is equal to 1/16? The answer is negative 2. 4 to the negative 2 power is 1/16, right? And so we'll do that again. Here we have 1/2 is equal to the log of base 36 is 6. So this is saying 36 to what power is equal to 6? The answer is 1/2, because 36 to the 1/2 power is in fact 6. So we've just rearranged the values to be in a logarithmic form. We can do the same thing here. We'll say that q, which is the exponent, q is equal to log of the base, which is p, of r, which is the power, right, the answer. And so p to what power is equal to r? P to the q power is equal to r. So the answer is q, because p to the q power is equal to r. This is example 2. It says write each equation in exponential form. So this time they give us 5 equations in logarithmic form, and they want us to write them in exponential form. And again, we just have to know that if x is equal to b to the y power, then y is equal to log base b x. And so again, we're just rearranging the values. We're just doing the opposite of what we did in the previous example. And so we have the logarithmic form already. And so b is the base, which is, in this example, 7. And we're saying that 7 to the y power is equal to 49. So log base 7 of 49 is equal to 2. The question being asked is 7 to what power is equal to 49? The answer is 2. That's exactly what we wrote. 7 to the second power is 49. So here we're saying that 4 to the third power is 64. Right? And so again, this is b, this is x, and this is y. And so I'm just rearranging those 3 numbers to match this form. Same thing here. This says that 10 to the negative second power must be equal to 0.01. So log base 10 is log base 10 of 0.01 is equal to negative 2. That's asking 10 to what power is equal to 0.01. The answer is negative 2. 10 to the negative 2 power is equal to 0.01. Here we have 27 to the 1/3 power is equal to 3. So the base to this power is equal to this number. And here we have m to the n power is equal to p. This is example 3. It says graph y equals log base 2x. And so they want us to do this by plotting points. In order to do this, the first thing we need to do is rewrite this in an exponential form. And so this says that 2 to the y power is equal to x, or that x is equal to 2 to the y power. And so we want to plot this graph by points. We'll look at x and y values. Now, it's going to make more sense for me to plug in y values, like possibly negative 3, negative 2, negative 1, 0, 1, 2, and 3. Plug in these y values and then solve for x. It'd be a lot harder to plug in x values and then solve for y, right? It's going to be easy to plug in these values for y and solve for x. And so I can start down here with 3. 2 to the third power is 8. 2 squared is 4. 2 to the first is going to be 2. 2 to the 0 is 1. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. And 2 to the negative third is 1/8. Right, so I would have never have guessed these numbers. Probably not anyway. I would never have guessed these numbers to plug in for x and then be able to solve for y. It's a lot easier to plug in numbers for y and then try to solve for x because of the form the equation is in. And so we want to plot these points on our graph. We've got the x-axis, we've got the y-axis. And so our x values go all the way out to 8. We also have 4, which is in the middle. We have 2, which is in the middle of that. And we have 1, which is in the middle of that. We also have 1/2, 1/4, and 1/8, which is very small numbers, right? I can hardly see those in there. And our y values range from positive 3 to negative 3, so 1, 2, 3, and negative 1, 2, 3. Okay, so this is 1, 2, and 3, and negative 1, negative 2, and negative 3. Okay, so when x is 1/8, y is negative 1/3. That's way down here somewhere, and it's very close to the y-axis. When x is 1/4, y is negative 2, about here. When x is 1/2, y is negative 1, so that's going to be about right here. When x is 1, y is 0. When x is 2, y is positive 1. When x is 4, y is 2. And when x is 8, y is 3. So I've just plotted these ordinate pairs, and we get an equation that looks something like this. Okay, and this will be the graph of y equals log base 2 of x. This is example 4. It says graph y equals log base 1/2 x. And so again, it's going to be a lot easier for us to do this if we first change this into an exponential form. The base is 1/2. The exponent is y. And this will be equal to x. And so we will plot some ordinate pairs. We have x values and we have y values. And again, it's going to be a lot easier for us to choose values for y because we can raise 1/2 to those powers and then figure out what x is. We don't want to make up values for x first and then try to figure out what y is. That'll be a lot harder. So we want to use values like negative 3, negative 2, negative 1, 0, 1, 2, and 3, and then figure out what x is. And so let's start down here with 3. 1/2 to the third power, that's 1/8. Right, 1/2 times 1/2 times 1/2 is 1/8. 1/2 squared is 1/4. 1/2 to the first is 1/2. 1/2 to the 0 is 1. In fact, any number to the 0 power is 1. 1/2 to the negative 1 power is 2. 1/2 to the negative 2 power is 4. And 1/2 to the negative 3 power is 8. And again, you can see the pattern here. 1/8 times 2 is a quarter. Quarter times 2 is a half. A half times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. Right? So that's how I knew these values. And so let's plot the equation here on our graph. We've got the y-axis and we've got the x-axis. And so our x values go all the way out to 8. And then we have a value for 4, which is right in the middle. We have a value for 2. We're going to have a value for 1. We'll have a value for 1/2, a quarter, and an eighth, right, which is getting kind of small in there. And our y values will range from positive 3 down to negative 3. Okay. And so when x was 8, y was negative 3. When x is 8, y is negative 3. When x is 4, y is negative 2. When x is 2, y is negative 1. When x is 1, y is 0. When x is 1/2, y is 1. When x is 1/4, y is 2. And when x is 1/8, y is 3. So this time we get an equation that looks something like this. This will be the graph for the equation y equals log base 1/2 x. This is example 5. It says given that log base 381 equals x, find the value of x. And so this is going to be easier if we first change this into an exponential form. And so this says 3 to the power of x is equal to 81. So the equivalent equation is that 3 to the x power equals 81. And so the question is well, 3 to what power is equal to 81? And we can do this by trial and error. Maybe you already know the answer, maybe you don't. So we can do it by trial and error. I'm pretty sure it's not 2, because 3 squared would be 9. Maybe it's 3. I'm sorry, 3. Is 3 to the third power equal to 81? Well, 3 to the third power means 3 times 3 times 3. Well, that's 27. So it's not 3, maybe it's 4. So 3 to the fourth power means 3 times 3 times 3 times 3. And that is in fact 81. And so the answer is going to be 4. X must be equal to 4. So again, if the log of base 3, 81, equals x, then x is equal to 4. In other words, the log base 3 of 81 reduces to 4. Example 6 says if log base 3x is equal to -2, find the value of x. And again, this is going to be easiest if we first change this logarithmic function into an exponential function. And so the exponential equivalent says that 3 to the -2 power is equal to x. It says that 3 to the -2 power is equal to x. And so we can find x now because we just need to find 3 to the -2 power. When the exponent is negative, it's the same thing as 1 over 3 squared. So if we have a negative exponent, we can move all of this to the denominator and change the exponent to a positive. And this will give us the value of x. And so 3 squared is 9. X must be equal to 1/9. And so this is saying that the log base 3 of 1/9 is equal to -2. Example 7 says if log base x32 equals 5/3, then find x. And again, this is going to be easiest to change this into an exponential form first. This is the same thing as saying that x to the 5/3 power is equal to 32. So I've just rearranged the values here to give me the exponential form. And so there's a couple of ways to go about this. First, if x to the 5/3 power, that is the same thing as saying the third root of x, all raised to the 5th power, is equal to 32. So when we have a fraction as the exponent, the denominator is the root index, the numerator is the power. And so to solve for x, we would start by taking the 5th root on both sides. The 5th root cancels to the 5th power. And so over here we're just left with the third root of x. And we need to figure out what the 5th root of 32 is. You could do this on a calculator. The 5th root of 32, that's the same thing as saying, well, what number, use a, what number to the 5th power is equal to 32? Well, it turns out the answer is 2. 2 to the 5th power is equal to 32, because 2 times 2 times 2 times 2 times 2 is in fact 32. So the 5th root of 32 is 2. 2 to the 5th power equals 32. The 5th root of 32 is 2. Now to cancel the third root, we raise to the third power on both sides. Right, so exponents are the inverse of radicals. So the third power cancels the third root. We're left with just x. X is equal to 2 to the third power. And so x is going to be equal to 2 times 2 times 2, which is 8. So x must be equal to 8. And so to restate the problem, the log base 8 of 32 is equal to 5/3.